All right, we're going to go over some problems for exam 2 review. And the first problem says, how many mils of 0.9401 molarity tin 4-chloride solution are needed to make 808 mils of a solution that is 1.3301 molarity in chloride ion? So for this question here, you need to know they're asking about chloride ion, and the source of the chloride ion is your tin 4-chloride solution. So they want to know how many mils of the tin 4-chloride solution you will need to make 808 mils of chloride ion that is 1.3301 molarity. So I would start with the chloride ion, use the molarity and the volume to get moles of chloride ion, and then I'll do the mole to mole ratio, chloride ion to tin 4-chloride, which is 1 to 4, SnCl4. 1 mole of that is to 4 moles of chloride ion. Then once I get the mole to mole ratio, I'll use the molarity of tin 4-chloride to get to the volume and then turn it to milliliters. So the first thing we do is 808.8 milliliters of the chloride ion. Turn it into, so this is Cl negative. I'm going to turn it into liters. And then I'm going to use my molarity that says it's 1.3301 moles of chloride ion found in 1 liter of the solution. And then I also know the mole ratio. I want to get rid of the chloride, so the mole ratio will go 4 moles of chloride ion is to 1 mole of SnCl4. And then after that, I know the molarity of SnCl4 is 0.9401. That means it's 0.9401 moles of SnCl4 to 1 liter. And then I can go 1 liter is 1,000 moles. That should give me the answer. So you put it straight in your calculator. You take 800.8 divided by 1,000 times 1.3301 divided by 4 divided by 0.9401 times 1,000. And it should give you the answer. And we would want to keep 4 sig figs here because there's 4, 5, and 4 sig figs. So I'm going to keep 4 sig figs and my answer should be 286.1. And the unit will be in milliliters. All right, the next question we have here is they gave us mass percent of a compound, and then they gave you grams, volume, pressure, and temperature of this gas. If you notice, this is P, V, and T. You should be able to solve for N, PV equals nRT. And you get, so number 1 is solve for N. And then we take the N, number of moles, and we use it with the grams here. We go molar mass of gas is going to be the grams that's given, whatever the grams is, divided by the moles of the gas that you calculate. That goes there. Okay, and then 2.046 goes there. Once you get your molar mass, you can get the molecular formula if you have the empirical formula. So number 1, we find the empirical formula. Based on these 2 parts, the carbon and hydrogen. And then once we get the empirical formula, we'll get the mass of the empirical formula. And then you take the molar mass, you divide it by the empirical formula to get your factor of how many times to multiply it with. So let's go ahead and get started. With this part, I have 85.61 grams of carbon, and I'm going to turn it into moles. Is 7.13. Let's see. 7.128. And then the next one, 14.39. You get 14.28 moles of each. So to get our ratios of the mole, you take 85.61 grams of carbon, and then 1 mole of carbon is 12.01 grams of carbon. So you take 85.61 divided by 12.01, you get 7.128 moles of carbon. You do the same process with hydrogen, 14.39 grams of hydrogen, but you multiply it with the fact that 1 mole of hydrogen weighs 1.008 grams. So the 1.008 grams of hydrogen is going to go on the bottom so they can cancel out, and you'll have your answer as moles, and you end up getting 14.28 moles of hydrogen. Once you have that, you can say C 7.128 is to H 14.28, and then you divide by the smallest number, and you get C is 1, H is 2. So this is my empirical form. So I need to find out how much that weighs. So C1 is, so empirical mass. So empirical formula mass is going to be 1 times 12.01 grams plus 2 times 1.008 grams. And you get 14.026 grams. So that would be grams per moles here for the molar mass, but that's the answer right there for empirical. And then we'll get our number of moles here, so we can get the molar mass, and we take the molar mass answer divided by 14.026 to get the factor of how many times we need to multiply CH2 by. So let's work on N. So P is 912.0 millimeters mercury. I'm going to divide it by 760 because I want to convert it to 18. So I'm just going ahead and say, okay, divided by 760. And that's a formula, so I don't have to worry about that. Sig fig, this is still 4 numbers here. And then this is an ATM. That's P. And then V is 0.7001 liters divided by R, 0.08206 liter ATM moles Kelvin. And the temperature was 6.85 Celsius, but we can't use Celsius. I'm going to make sure I change it to Kelvin, plus 273.15. You put this answer in, and let's see what we get for the calculation for moles. You end up getting 0.0365 6 and then 38. It keeps going, but we only need 4 here at the most. So we take that number and you put it over here. So this little moles here, it's going to travel all the way and put that there. So it's whatever the moles is, I guess 2.046 divided by 0.03656, and you get your molar mass to be 55.96. And then once you get your molar mass and your empirical, you can work on it to get the N factor. So you take the molar mass divided by the empirical, and you get 55.96 divided by 14.026, or really 3. And the factor you get there is 4. So that means CH2 must be times with 4. So your answer is C4H8. That's the empirical formula. But once you get the molar mass, you divide it by the empirical mass. You know how many times to multiply it with, and you get C4H8. Okay, let's take a look at the next question. You have 171 mils of 0.2422 molarity silver nitrate. And then you have another solution, 104.89 mils of 0.1427 molarity ammonium chloride. And they're going to mix together, and then they say how much silver chloride can you make. So they're asking for how much product, which how many grams are formed. This is going to be asking for the theoretical yield. That means you take the amount of the first and you take the amount of the second, find out each one how much AgCl they can make. And the smaller number is the theoretical yield, because once you finish using up the first ingredient that runs out, you can't make more. Okay, that's the limiting reactant. So let's go ahead and get started. We'll do 171.75 mils. 1 liter is 1,000 mils. Our molarity is 0.2422 moles of AgNO3 to 1 liter. And then we know the ratio, 1 mole to 1 mole. 1 AgNO3 is to 1 mole of AgCl. And to get to grams of AgCl, you really need the molar mass of AgCl. So if you take Ag from the periodic table plus the Cl from the periodic table, you get 107.9 plus 35.45, you get 143.35. So I'm going to just put that down, 143.35 grams of AgCl. So that should give me a number. And I'm going to do the same thing for the second reactant. And then I'll pick the smaller answer as my theoretical yield. So I'll set it up the same way. So everything's the same. I use the volume in milliliters, 104.89 mils divided by 1,000 mils because I want to change it to liter. And then you multiply with the molarity number, 0.1427 moles to 1 liter. And the mole ratio again is 1 to 1. So 1 mole of NH4Cl is paired with 1 mole of AgCl, where 1 mole of AgCl weighs 143.35. So you put this in your calculator. For the first step, you do 171.75 divided by 1,000 times 0.2422 times 143.35, and you get 5.962 grams of AgCl. And then you do the same for the second reactant, 104.89 mils divided by 1,000 times 0.1427 times 143.35, and you'll end up getting 2.146 grams. So again, I picked a smaller number. That's my theoretical yield of 2.146. And my limiting reactant would be NH4Cl. My excess reactant would be AgNO3. All right, next question. How many milliliters of iron 3 chloride solution are needed to react with an excess of Li2S to produce 0.3659 grams of Fe2S3 if the percent yield for the reaction is 59.88%. And they give you a reaction here is 3 Li2S plus 2 FeCl3 equals to Fe2S3 plus 6Cl, 6 LiCl. So it's balanced, and they even give us a molar mass of Fe2S3 is 207.91 grams per mole. So again, I like to look at what are they asking for and where should I start? So if they're asking for milliliters of a solution, I will use this molarity at the end to turn into milliliters, but to use molarity to turn to volume, that means I must somehow find the moles. Okay, so I need moles of FeCl3, and it says they have excess Li2S. That means the mole ratio of FeCl3 can directly be linked to the moles of Fe2S3. So if it were 100% 1-to-1, it would be 2-to-1 ratio. But this reaction is 59.88%. So you know 59.88% yield is only yielding 0.3659. What's 100%? Because we need 100% to do our math. So I'll say, well, let's look for 100%, however many grams that is. Now turn it to moles. Now do the mole to mole ratio to FeCl3. And then I can use the molarity to get the volume to liters. And then I can get it to milliliters. Okay, so let's get going with the math here. I'll start with, I have 100%. I need 100%. I know that 59.88% is 0.3659 grams of Fe2S3. So, and then we do the mole to mole ratio. Draw the line a little longer. So we have still grams. Let's get to moles. And then we do the mole to mole ratio. So 1 mole Fe2S3 is 207.91 grams. And I know that the mole ratio is 1 mole of Fe2S3. See, 1 mole to 2 moles to 2 moles of FeCl3. And then you use the molarity of FeCl3, 0.2310 moles of FeCl3 is to 1 liter. So 1 liter is 1,000 mils. That should give us our answer. So you put it in your calculator, you take 100 times 0.3659 divided by 59.88 divided by 207.91 times 2 divided by 0.2310 times 1,000. And it should give you an answer of 25.45, and the unit is in milliliters. Okay, so that's 4 questions. Let's go to the next question. So next question is a Hess's law question. I'm going to give you 4 equations and tell you to use those to match the one on top. So with the Hess's law, you always look for the pieces that don't repeat itself. To start there, and then you try to put the jigsaw puzzle together. So when I look at line 1, I have P4 and then P4 appears again. That's confusing. I have Cl2, the Cl2 appears again. That's confusing. I have PCl3 and it doesn't appear again down here. Oh, actually it does. Yeah. Okay, well, that's not good. This one repeated, this one repeated, this one also repeated. So it's going to be one of those that's confusing. So I would skip line 1 for now. We'll come back to it at the end. So let's take a look at line 2. We said P4 was confusing. We want to stay away from that. O2, it was, does it repeat? O2, yep, it does. It repeats. And then P4, O10, does it repeat? Nope, P4, O10 doesn't repeat. So your only chance to use P4O10 is now, because it doesn't happen again. So if you have P4O10 on the product side and you need P4O10 on the reactant side, all you do is flip. And the moles is, once you flip, is 1 mole and you have 1 mole on that side. It's correct. So you don't have to multiply with a number. So I said line 2, we just flip the equation around. So we write it again. P4O10 is P4 plus 5O2, and my delta H would be flipped the sign, positive 2973.7. Okay, let's go to line 3. On line 3, PCl3 repeated, I don't want to use that. Cl2 repeated, I don't want to use that. PCl5 does not repeat, so I can use PCl5. If you take a look at your option of PCl5, right now you have it on the product side, just 1 mole, but you really need it to be on the reactant side, and you need it 6 moles. So you should flip it and get it to the correct side, but then you also have to times 6 to get it to the correct number. So when you do that, line 3, you get 6 PCl5 goes to 6 PCl3 plus 6 Cl2. And your delta H will be flip the sign, so positive 92.4, and then U times with 6. So far, I've matched P4O10 to P4O10 here. And then the next thing I matched was 6 PCl5. The last thing I want to do is that guy, Cl3PO. Do I see it? Yeah, I do. I see on line 4 and it doesn't repeat anywhere else. So that's my only chance. So I have one on the wrong side, basically. And I need, actually on the correct side. This is product, but the wrong number, right? I need 10 times of it. So you'll actually take line 4, just keep it the same side, times 10. So when you do that, you get 10 PCl3 plus 10 times half would be 5 O2, and then you get 10 Cl3 PO. And your delta H would be 10 times, stay the same sign, negative 277. I'm gonna box this up and say, oh wow, look, I got my pieces that I need, but I think I have a bunch of extra stuff floating, right? Yeah. Let's see if they cancel off. So if you write all the reactants and all the products on one side, and then you can cancel off things that repeat. 5O2 is very obvious, it cancels off. And then so that's good. But then you're like, what about the others? I have P4, it has nothing to cancel off with. And then I have 6 PCl3, but then I have 10 here. It doesn't quite cancel. I tend to have 4. And then I have 6 Cl2, and where does that go? So that means you're not done. So you need to take a look at the last line remaining, which is line 1. And the most obvious thing is P4, you got to get rid of. You need to get rid of PCl3, but then there's 2 of them here. You technically have 4 PCl3 you have to get rid of, and you have 6 Cl2 to get rid of. So the easiest one out of these 3 options here is to look at P4 to get rid of, okay? So you need to look at line 1 and say, is there a way I can use line 1 to cancel off 1 P4? You say, well, if I times this one by 4, I'll get P4 on the reactant side. It could cancel with the product side P4. So I'm going to do that. Line 1, I'll actually keep it the same way, but times 4. So when you times 4, you get P4 plus 12 over 2 becomes 6 Cl2 goes to 4 PCl3. And then your delta H would be 4 times negative 2, negative 312.0. So then you revisit your groups again, see this time, does it cancel off? Then you see, oh, look, there's 4 and 6, that adds up to 10. And I can cross off my 10 PCl2. And then you see here, there's a 6 Cl2 and a 6 Cl2 that cancels off. And the P4 cancel with the P4. So if you take one easy one and match that, it should all fall into place. Now that you know that it all cancels off and you get your required thing and all the extras are gone, you know the answer is okay because you get P4 O10. And then plus 6 PCl5 goes to 10 Cl3PO. And your delta H will be all these 4 numbers added together. You should get negative 490.5. Let's do number 6. All right. Use the delta HF and delta HR reaction formation provided to calculate delta HF for SO3. So you need SO3, you need to find out what SO3 is, but they gave you the reaction and they gave you the answer for SO2. This is given. So you know the formula. Negative 218.7, the delta H reaction is the total of products minus the total of reactants. What is this value? This is 0. They don't have to give you this because it's the most stable form of that element. So you get a delta H formation of 0. So that would be 218.7 negative. That would equal to 2 times SO3's number, which is my unknown. I'm going to call it X. And then it will be total products minus total reactants, which is 2 times SO2's value, negative 297.3. And then that's a 0, so I don't have to worry about it. So let's solve for X here. X is my SO3. So when you do that, you get 2x equals to negative 218.7. And then because it's minus, we plus both sides with 2 times negative 3. And then to get just the x, you take the whole thing divided by 2. And you get x to be negative 406.7 if it's 1 decimal place. All right, let's go to the next question, number 7. For number 7, what we have here is a coffee cup calorimeter question. There's a piece of metal that's hot. They put it in a cup of water that's a little cooler. And then the end temperature is kind of in the middle. So the water warms up, the metal loses heat. So assuming no heat is lost to the cup, what is the specific heat of the unknown metal? So you know there's a unknown specific heat. So you have 2 things. You have Q of water, and that's M CS of water, delta T of the water, and then you have Q of metal. That's M of the metal, CS of the metal, delta T of the metal. And these two are opposites. In fact, I can tell by looking at temperature because the metal cooled down, the metal is going to be a negative number and the water is going to be the positive number. So what I'm going to do is I know I have every part of the water's component. I have the mass because if I use the volume of water, the density of water is 1 grams per mil. I know the grams of water. And then the CS of the water is given. And then I have the delta T because it's final minus initial temperature. So I can get everything a Q water. Once I get a Q water, I say, well, that's the negative sign for the Q metal. It's like one of them is negative. So Q water is positive, Q metal is negative. And to set them together, Q water equals to negative Q metal, just because one's the opposite sign. So I'm going to go ahead and solve for water. And then I'll put the missing pieces in here, the mass of the metal, delta T of the metal, and we can solve for the CS of the metal. That's what's being looked for here. So Q water is 83.8 grams of water because 83.8 mils is 83.8 grams because density is 1 grams per mil. And then times 4.18 joules per gram Celsius, heat capacity of water. The temperature, remember delta T and delta C, delta Celsius, delta T in Kelvin or Celsius, it doesn't matter. It's the same number. So I'm just gonna take the values here. The final was 326.88 minus the initial of the water was 299.42. This here is my delta T. In Celsius or Kelvin is the same answer. Okay. And then that one's a CS of water. This is the mass of water. So when you solve for the Q of water, you get an answer. It's positive 9618. And then I'll just keep writing a bunch of numbers, but you don't need to. You can just keep it on your calculator and then put a negative sign on it. In fact, we're only at 3 sig figs. But let's switch the sign and say, okay, well, Q metal is the opposite sign. So water is positive, Q metal must be negative. Negative 9618.79864. Just a long number. That equals to mass of the metal, which is given as 28.34. So I'll write it down. CS of the metal is what we're looking for. And then the temperature is final is 326.88 minus the initial of the metal is 399.86. Again, that's the delta T for the metal, CS of the metal, mass of the metal. And you have to answer from the water, flip the sign, solve for what CS is. So if you put it in your calculator, what you do, the negative, whatever the number for the joule is, put a negative sign and then divide it by 28.34 and then divide it by the delta T here. You should get your CS of 4.64. And the unit will be like, joules, grams, Kelvin or Celsius, doesn't matter. But you just type in 4.64 as your answer. All right, let's keep moving. Number 8. This is a bomb calorimeter question. Bomb calorimeter where they take sucrose and they burn it. And then the sucrose combustion is exothermic. So it will be a negative reaction heat. And then the bomb calorimeter absorbs that heat and it raises in temperature. And then they give you the heat capacity to calorimeter is this number. So if you take the C of the calorimeter and the delta T in the calorimeter, you can get the heat of the calorimeter, which is then the negative, the opposite for the heat of the combustion. And then if you get the negative, then you just put in the whatever the energy is. that would be in joules. And then you just find a way, they say they want it to be in kilojoules per moles. Then you just find a way to take this into kilojoules and then you divide by moles of sucrose. Now you're like, where do I find the moles? Well, that's because they give you the grams of the sucrose. And if you give you the molar mass of the sucrose, you just find the moles of sucrose. That's what you divide by, the number there. Okay. So let's go ahead and calculate the Q-cal, and then we'll plug it in and then find the moles of sucrose and then divide it to get the correct answer that's being asked about. So Q-cal equals to C-cal, which is given 18.87. Well, actually, they gave us kilojoules per Celsius, so your answer is going to be kilojoules. And then the delta T is 29.80 minus 10.18 Celsius. And you get 370.2294 kilojoules. I don't round it on the calculator, just leave it there. And then you keep going and you say, well, this is in kilojoules, but I need to divide by the moles of sucrose. So how do I get the moles? I just say, well, 226.04 grams of sucrose. And the molar mass is 1 mole is 342.3 grams. We'll keep 4 sig figs here. Obviously this one too, you'd be keeping 4. 4, the 5th number, sorry. So 4 sig figs, that one there. Get the moles of sucrose, 0.660356 or 2 moles. But you really only need 4 numbers. So 6604. But you just take the whole number, you take this kilojoules divided by that. And just remember the Q reaction is going to be negative. So let's write it down first, negative 370.2 kilojoules. And then you divide it by the moles. So the delta E reaction is the same as Q reaction. And that is negative 370.2 kilojoules divided by 0.6604 moles. I really just don't round until all the way to the end. I keep all the numbers on the calculator. And then you end up getting, with 4 sig figs, 560.7, and it's a negative. And that would be for units of kilojoules per moles of sucrose. And you gotta always double check that you get a negative answer because it says combustions or exothermic reactions, and you should know that. And they ask for the combustion heat, so it should be a negative sign. All right, let's keep moving. Let's do number 9. Number 9 here, we have a reaction to form gas, and they say, oh, we're going to collect this gas over water. Every time you see gas collected over water, remember this. The P total that's given is actually a combination of the P of the gas, whatever the gas is, plus the P of the water vapor. And they'll give you the water vapor pressure. See, they gave that to us. So this today for us is 29.873 torr. And then P gas, our gas is H2. So the total pressure it's given to us is 735.210 torr. So P of the H2, which is our gas, is actually 735.210 minus 29.873 torr, which gives us 705.337. Okay, and if you want to get use this pressure here, what are they asking for? They said how many grams of zinc have been consumed, assuming 100% yield. So they said I got this much gas made. Can you tell me if it's 100% yield, how much zinc did I start it off with? So the most important thing is to get the moles of hydrogen. Once you get the moles of hydrogen, you do the mole to mole ratio. It's the same mole, 1 to 1. Then you say, oh, okay, once I know the moles of zinc, I can just use the molar mass of zinc and I can get grams of zinc. That's 4. You don't have to worry about the changing the yield because it says assume 100% yield. So over here, let's go ahead and get started. Find the moles by using PV equals nRT, where moles of hydrogen gas is going to be PV over RT. So I'll take the P. You gotta divide by 760 to make ATM units. And then the V has to be in liters unit. Divide by R. And then the temperature that was given to us is 28.90 Celsius, but we gotta convert it to Kelvin. Okay. So on your calculator, what you're going to do is take 705.337 divided by 760, get the pressure, times 0.1881 liter. And then you're going to divide by 0.08206. And then you got to make sure you divide by the total of these two numbers added together. So be careful when you set it on your calculator to take the top stuff as multiply and then divide. And then you can hit divide again by the answer of this. Or if you want to do the two parts on the bottom, don't forget to put a parenthesis around it and say this times this, and then put a bracket on the outside on your calculator. Okay, so double check. If you put this in your calculator correctly, you're going to get a small number, 7.043 times 10 to the minus 3 moles of H2. And then you're like, okay, once I get moles of H2, I actually can keep going because, so I'm going to keep going here. Because remember we said once you get moles of H2, you can get moles of zinc because it's 1 to 1. So 1 mole of H2 is 1 mole of zinc. And then I'm going to use the molar mass of zinc. 1 mole of zinc weighs 65.39, which is given in the question, grams of zinc. That should give me the grams of zinc. And I want to keep 4 sig figs, so 0.4605 grams of zinc. Just the numbers, you see, 4605, 0.4605. All right, let's keep going. This question here is a partial pressure question. They have 3 gases. They give you the mole fraction of 2 of them. If you know 2, you can find a third one because the total is 1. Okay? And they say if the mixture is at STP, remember STP has molar volume, right? 1 mole of gas at STP is 22.4 liter. So this one here, you'll end up being 3 sig figs here. So, and we have 3 sig figs here, 3 sig figs, 3 sig figs. So your answer is probably going to have 3 sig figs, but it's going to be in scientific notation, okay? Because they said instead of asking you for usually the moles or the grams, they're asking you for molecules of CO2, okay? So you're going to use Avogadro's number. But let's find out CO2's mole fraction because you have the 2 gases. So 1 minus 0.144 minus 0.457 gives you 0.399. And this one here is the mole fraction. Right, symbol this CO2. Okay. Once you get the mole fraction, you need to know, okay, this is 0.399. And they're asking how many moles of CO2 are total are present. Did you know that the total here is 36.6? So 36.6 liter Okay. And then you go, okay, that's for the total of all the gases, right? That's for the total of all the gases, which is 1. And the portion that we're interested in is 0.399 because we're interested in CO2. So now I can essentially get the volume that the CO2 technically takes up, okay? Which tells us the moles because 1 mole takes up 22.4 liter. So see how the liters now cross off in the mole fraction. So you just gotta make sure you get just the carbon dioxide part. And then you get, well, 1 mole of gas is 6.022 times 10 to the power 23. So what is 2? And this is total. Okay. So if you put in your calculator 3.36.6, and then you times 0.399 divided by 22.4 times 6.022 to the power of 10 to the power of 23, you should get your answer. And we want to keep 3 sig figs here, 3.93 times 10 to the power of 23. And that should give us molecules of CO2. Okay, let's keep moving. We're going to go to number 11. Number 11, it says the molar mass of the unknown gas. So it's asking you to do molar mass of a gas. If they give you, ask for molar mass and they give you milligrams, you can use that to be grams because you turn it grams and the rest of the part is the moles. So to find the moles of the gas is PV over RT. Remember the units that you need. P will be in ATM. So divide by 760. And then V is in liters. R is the gas constant provided on your periodic table. And then delta T, just T, not delta T, 71.33. But you can't use Celsius, so you have to plus 273.15. Now put this in your calculator. You would do 565.9 divided by 760 times 0.4533 divided by 0.08206 and then divided by the total of 71.33 plus 273.15 and you end up getting 0.01194 moles. And we say the molar mass would be the grams. So if you take 343.66 divided by 1,000, because it's milligrams to grams, 0.34366 grams divided by 0.01194 moles. And you end up getting 28.78 grams per moles. All right, let's do the next question, number 12. Number 12 is asking for you to do the density of a gas. So density of gas, you can do STP is easier, and then there's a regular one or non-STP. STP, you just gotta remember 1 mole of gas is 22.4 liter. So your answer, if you have to do grams per liter here, you're gonna pick 3 sig figs in your answer. Okay, so what you're gonna do here is do 1 mole of gas is 22.4. So you know the liters, and then you find out how much 1 mole of gas is in grams. Well, that just means molar mass. So let's find the molar mass of this. So C8, so 8 times 12.01 plus 25 times 1.008 plus 3 times 16.00. Add it up. You get 169.28 grams per moles. And then you go, density would be 169.28 grams divided by 22.4 liter. You get 7.56 grams per liter. All right. The next question here is a gas question still, but it gives you a balloon and 2 scenarios. You have temperature 1, volume 1, pressure 1, temperature 2, pressure 2, look for volume 2. So you got to remember P1 V1 over T1 equals to P2 V2 over T2. So remember, the temperature must always be in Kelvin. You can't put Celsius on the bottom. So let's set up the calculation here. The first pressure is 0.8175 atm. And then the liter is 7.373 liter. Temperature must be in Kelvin, so take 17.41 plus 273.15. That's in Kelvin. That equals to P2, 7.747 atm over V2 that we're looking for, divided by the new temperature, 187.71 plus 273.15. And then you solve for V2. So if you rearranged it, you really would do, I'll write it out, 0.8175, 7.373, and then you'll multiply with the temperature T2 here. And then you would divide by 17.41 plus 273.15. And you divide by 7.747. That should give us V2 in liters. And then you take that times 1,000 to get it in milliliters. So if you put this in your calculator, you take 0.8175 times 7.373 times the addition of negative 187.71 plus 273.15. And then you divide by the total of 17.41 plus 273.15. And then you divide that again by 7.747. You should get 0.2288. And times 1,000, you get 228.8 moles. All right, let's keep going. We're doing number 14. Net ionic equation. Okay, so there's complete, there's net. So you have to see, okay, this is double displacement. If I put K2S equals, and then FE2, no, F2, FeNO3 2. You mix it up. What do you get? KNO3, and then Fe and S. If you check your solubility rules, this is a solid. So that means this is the key to my balance net ionic equation. But let's just double check to make sure it's balanced. You put a 2 here, 2, 2K, 1 NO3, 1 and 2 NO3 here. That's good. And Fe, 1 Fe, 1 S. So that's balanced now. So the spectator ions are going to be here. K plus. And then I guess I'll write a complete ionic and then show you that. You don't have to do this on a real test because you would be wasting time if they're asking for net ionic, don't worry about doing everything. Just go straight to Fe2 plus S2 minus goes to FeS. That would be the net ionic. But just for fun, I'm going to write the complete too. Okay. So there will be S2 minus plus Fe2 plus 2NO3 goes to 2K plus 2NO3 plus FeS. So you see how the spectators are crossed off. And then you have the net ionic equation left behind. All right, let's look for the reducing agent. The reducing agent means you gotta find oxidation state of everybody, find out who's oxidized, who's reduced. This Al is 3, Fe is 0, Al here is 0, Fe is plus 2. So 3 going down to 0, that's being reduced. This is the oxidizing agent. Okay. Fe going to Fe2 plus is being oxidized. That means this guy here is the reducing agent. Fe is the reducing agent. Okay. 3 flasks with 3 gases at the standard temperature and pressure. So at STP, that means they have the same temperature and the same pressure. Okay. And it says these are the gases. Actually, it's not 3, it's actually 4, right? Flask B. Yeah. Flask A has something, B has something. But there's 4 flasks. Which flask contains the largest number of molecules? Well, if they're all the same volume, same temperature, same pressure, wouldn't they all have the same moles? Right? This is constant, and then temperature is constant, obviously gas constant is constant. That means the N is also constant. So everybody has the same number of moles, which means everybody has the same number of molecules. All right, number 17. Let's take a look at this question here. They say I have combustion reaction. Delta H of the combustion is here. Can you find out how much heat is associated if you make 100 grams of CO2? They gave us a molar mass of CO2, so that makes it a little easier. So you just want to get grams and then the molar mass to get moles of CO2. And then you know from this equation, 16 moles of CO2 gives off negative 11018 kilojoules of heat. So that's where you start, and then you find out how many moles. So you start 100 grams of CO2, turn that into moles. And then we say 16 moles of that is to negative 18 kilojoules. And calculate the heat and keep it in kilojoules. That should give us the answer. So you take 100 divided by 44.0095 divided by 16 times negative 11018, and you get negative 1565 kilojoules. Okay, let's keep going. We got 2 questions here about quantum numbers. It says here 2p. How many mLs are possible? So what is 2? This is n is 2. P means L is 1. So if n is 2, L is 1, what are my mL options? -1, 0, +1. So there's 3 different values. And that's why there's 3 types of 2p orbitals. 2px, 2py, 2pz. And the next question it talks about is which transition represents emission? Emission is coming down, absorption is going up. So we're looking for something coming down. And we're gonna remember that the first levels are really big gap, and then get smaller gap, and then even smaller gaps, and then even smaller, and then even smaller. So and 1 and 2 and 3 and 4, 5. Just showing you as you keep going up, the closer it gets together, okay? So emission means it must come down. So going up, that's wrong. Okay, I got 3 of them coming down, 4 to 3. And I got 5 to 4. And I got 3 to 2. Okay, so they're all different sizes, and they say the longest wavelength. The longest wavelength is going to be the smallest energy. So the smallest energy gap would be 5 to 4. Okay, they could ask you in frequency terms or energy levels. So just make sure you know the relationship. High energy, high frequency. Okay. And small wavelength. So wavelength is always the opposite. If you're looking for low energy, you got low frequency, but the big wavelengths. Okay. All right. Let's go to our last question. Our last question is arrange these electromagnetic radiation in decreasing energy. So you should not arrange them increasing, decreasing, different types of radiation and different colors of the visible light. So just don't forget, sometimes people forget like they talk about like UV light versus IR. Just remember UV is higher energy. So violet is close to UV. So violet, purple is higher energy. And infrared is weaker because you can shine infrared on your body for thermometers. So infrared is lower energy and red is the weaker color. So purple is the higher energy color, red is the weaker energy color. And then on here, gamma ray is the strongest. So gamma ray goes first, highest energy. And then the next one is microwave. And then on the next one here is radio waves. So make sure you memorize the electromagnetic spectrum. Okay, but that's it I have for exam 2. Good luck studying.